okay. It's pretty.
Okay. Here's your candy for this. Sorry. All right, I'm gonna try to get all the subscripts straight today. What I found was one, as far as I can tell, there is one case where Weinberg gets sigma and sigma prime mixed up. And so I printed this out and put it on the web. If you see any typos, let me know, because we want to get this straightened out. This is, by the way, this is the most technical thing that we're going to do this year, almost. So it's essentially downhill from here. Yeah.
When you say year, is there going to be a quantum field theory too?
So, well, if I'm assigned to it, I'll teach it if there are students who don't take it. That would be, I would be focusing more on the Z book because Z has a much broader range than Weinberg in his one. Okay, so what we've got here, what we know here is how states transform, and we worked through this. This is lambda P0 over P0, a sum sigma prime Ej sigma prime sigma bigger rotation lambda P, the state lambda P spin sigma prime. Okay, so this is all for massive particles, and we're going to stick to massive particles certainly for today. And because W is here, L inverse of lambda P, lambda L of P. And L of P is the thing that takes you from K to P, where K is just M0. Okay, so that's basically it. Everything, the idea is, the vacuum is thought to be a state that's totally invariant. Of course, this is in flat space, we're not doing cosmology. The state P sigma is a creation operator, A of P sigma, on the vacuum. And so the upshot of this is, and in fact, let me just skip and put in translations also. It would be U of lambda and B. I'm using B instead of A momentarily because the annihilation operators are A. So U of B, U of lambda and B, the creation operator, A of P and sigma, U inverse of lambda and B. Now this creation operator is the thing that replaces the vacuum by the one particle state, or equivalently takes the n particle state and adds the particle P sigma. So in other words, A dagger on P sigma, of P sigma on a state P1, Pn is P sigma P1 dot 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 Pn. Okay, it adds one particle, and the notation we're using is that it puts the label in the front. And for fermions, that makes a difference of a minus sign. For bosons, it makes no difference. So consequently, this is the square root of lambda P0 over P0, sum sigma prime dj sigma prime sigma of W, a dagger of lambda P sigma prime. So that's how this translates to creation language. And let me see, I've actually left something out. There's a phase factor. And the phase factor, I see I've got the phase factor wrong in some of these equations. Damn it. Okay. All right, let me redo. Where is it? This is just the A and B. I wanted to use B to avoid having A stand for two different things, but I think I'm just going to let A stand for A as it is. So this is a Lorentz transformation lambda followed by a translation by A.
Can we not use A? That's just going to be so. It's going to be so confusing. Using A.
Two A's?
Yeah.
All right, I'll use B.
We can use T or something.
Yeah, that's right. Okay. All right. So what this is? This is a dagger. Then this is supposed to be e to the minus I lambda p dot b. I originally had b in equations 8 and 9, and then I realized that I wound up, after I changed to A, later on I'm going to change to A. Okay? But by then you won't be confused. Okay, so that's for the creation operator. For the annihilation operators, U of lambda b, A of t and sigma, U inverse of lambda and b is e to the I lambda p dot b, square root lambda p0 over p0, sum sigma prime, dj sigma sigma prime. This was sigma sigma prime, actually. Wait a minute, it's sigma prime sigma initially. Right, okay, I shouldn't be skipping equations here. W inverse A of lambda p sigma prime. I don't know, maybe I shouldn't have skipped. All right, you guys have the notes in front of you, so let's look at equation 8 and what are we doing? First, we act with the Lorentz transformation that changes p into lambda p. So then the translation by b gives you a factor e to the minus I lambda p dot b. That's in the creation case. On the other hand, let's see, maybe I should do the thing with, do you want me to do it on the board with all the equations and not skip anything?
I mean, like deriving these two? I think
Yeah.
it's straightforward. I mean, we did it last.
Yeah, I don't.
Yeah, we did it last.
You can probably just go
It's
into
fine,
the
yeah.
field.
All right, all right, let me just put in a little bit. The first thing is we have dj sigma prime sigma, and that comes from this. But then we say that of w is d adjoint sigma prime sigma of w inverse, because the adjoint represents the inverse matrix. And then the adjoint is nothing but d star of sigma sigma prime. So that's the trick on the top line. On the bottom line, well, we first take the adjoint. Well, it has to be the adjoint of the other one. And it has to be simply the complex conjugate of the other one. It's the adjoint of the equation, but these guys are just complex numbers, so you just get a complex conjugation. So consequently, when we get to, all right, let me get to the right part of this stage. If we have dj star of W inverse, it's sigma sigma prime. And so now if we take the adjoint of that equation, we get a plus sign here, and here the complex conjugation goes away, and we simply get that. So those are equations 8 and 9. Now, how do the fields transform? Well, we want the field, we're writing the field, first of all, as the sum over sigma. I dropped.
Like Kevin?
Yeah.
Is there, so that D star, is that W or W inverse in there?
Where? Here?
No, over,
This is W inverse.
below that? There's no argument there. What is that?
Yeah, I know. All right. So what was I saying here? dj of sigma is the adjoint of that, and therefore this is, right? Because if you take the adjoint, it's the complex conjugate of the transpose. Okay, so we're writing the fields. Weinberg also sums over particle type, but I think that adds unnecessary complexity. It has an advantage, but I don't think it's worth the cost. So this is some UL that depends on X, P, and sigma, and then this will be. So the basic thing. Remember, I said to you the quantum field theory is based on very few ideas. One of them is special relativity, which we're going through today. Another one is simplicity. Another one is the idea of fields. And then simplicity. The fields are just linear combinations of annihilation and creation operators. The annihilation operator is just the adjoint of the creation operator, and the annihilation creation operator just map states into other states. But they don't tell us what any of these states, anything about what the particles really are. And so it's a sort of high-level description of stuff that we don't understand. But since it obeys quantum mechanics and relativity, it gets us a long way toward being able to predict the results of the gross results of experiments without understanding really what anything actually is. The negative frequency part of the field is then a sum on sigma integral dqp VL of x semicolon p sigma, and I'm going to put a different. See, Weinberg just keeps A, but he has this x index n. So what he has is, when he gets serious and represents a particular field like the electron, he has in the positive frequency part, n occurs for, say, the electron, and in the negative frequency part, n doesn't occur for the electron; it occurs only for the positron. Now, you might, all right, so let me, a brief digression, something that I said last time, or time before last, but that's very important. It turns out, of course, or in fact, if you think about it, psi plus L, psi plus of Y adjoint, commutator or anti-commutator, in general is not zero, even for x minus y squared positive. And the same thing with a minus here. So we can't use we can't use separately the positive and negative frequency parts of the field. We're going to have to define the field as some kappa psi L plus of x plus lambda psi L minus of x, and choose K and L so that we have psi L of x, psi L prime of y, commutator or anti-commutator, whether or not we have a dagger there, well, no, let's just leave the, yeah, all right, whether or not we have a dagger, we want this to be 0 if x minus y squared is greater than 0, that is space-like. So we want the fields to commute or anti-commute at space-like separation. And the only way to do that is to take linear combinations. We'll get to that next time. Okay, I've got to give David here a handout. Unfortunately, I got A and I used B when I should have used A, or A when I should have used B a little bit, but those are just translations, so we finesse the translations. Yeah.
What did L stand for again? You have psi sub
Oh, L is simply an index on the spinner and on the field.
Okay, so what is it like? What is it indexing?
Well,
Is it indexing?
it's
like
just
components of the
indexing.
spinner?
All right, I mean, most people think of it as spin,
Okay.
but it's not really spin.
Yeah, I thought sigma was the spin.
It's like spin.
Okay.
All right, but good question here, since I have Candy. Like David, you probably asked a question. Okay, so what you do is you choose, we're going to choose, not today, but next week, kappa and lambda, so as to have the fields commute or anti-commute at space-like separation. This gives us causality, but it also, as Weinberg says, gives us cluster decomposition and so forth. But now, let me focus on this why we've got antiparticles coming in so soon. And the idea is that suppose, in fact, let me get the signs right here because it'll be less confusing if I have the signs right rather than wrong. All right. So suppose we have Q annihilation operator AT sigma to be minus Q A of P and sigma. So that means that if Q acts after the annihilation acts, the charge of the state goes down by Q. And one would also have then Q a dagger of P and sigma. That's minus the adjoint of this, so this would be Q a dagger of P and sigma. So the creation operator increases the charge of the state by Q. Okay. So, where are we then if we have something like psi? What we want is Q psi to be minus Q psi. That is to say, we want, if we use psi plus simply, we see that the A's should lower the charge of the field. I mean, lower the charge of the state. But if we want this, and we also are saying that this is Q of, say, kappa psi plus lambda psi minus, but we know how these behave. The psi plus would have a Q, so this would be KQ psi plus minus, or kappa Q minus lambda Q psi minus. Okay? So we see that when we put the psi plus and the psi minus together, we can't use the same annihilation on creation. Are you asking a question?
Never mind. I think you're answering it.
Oh, here, for the intention. So, what we have to do is we don't just take psi plus and psi minus, we take psi plus and the negative frequency part for the anti-field. In other words, it's got to be psi plus L, let us say. I left out the L's. L, and I'll put a super Q, and here minus Q, corresponding to that minus Q. And then this will be minus Q, or wait a minute, this will be, yeah, this, I got it wrong. This is a minus and that's a plus. And if we want this to be minus Q psi L, this being Q psi L, we want that to be minus Q psi L so that the field lowers the state, the charge of the state Q. Then the field has to be a linear combination of the positive frequency part for particles and the negative frequency part for antiparticles. So in other words, QA, some state Q is oh, I've got this wrong. It's QA, some state of charge, big Q prime, let us say, is big Q prime minus Q times the state Q prime, and QB Q prime is Q prime plus Q on the state Q prime. On the state B Q prime. Well, there should be an A here.
So this charge operator is like a number operator.
Yeah, the number, it's a number of charged particles, effectively, of particles of a particular kind. And so if we're going to have the field transform, the field change the charge in a nice way, then we've got to have antiparticles. And we have to, the field then has to be, the negative frequency part has to have the p daggers in there. Of course, the field is neutral, then you might as well have a dagger. And this is in order to have a theory that conserves charge. And normally we think of electric charge, but in particle physics there are many different kinds of charges. And by the way, the thing that conservation of charge is probably measured more exactly than almost anything else. All right, so how the fields transform. Well, these are the fields, and these are antiparticles. That's why I'm using B there instead of A. And so then what we have is U of lambda A on psi L plus of X. U inverse of lambda A. Now A is the translation, so this is just some 4 vector. And this is the sum over L bar. Actually, I have plus. So the idea is we first do a Lorentz transformation. That takes psi of x into psi of lambda x. Then we do a translation by A. And now, this is then sum on to L bar dl, L bar of lambda inverse. So these are square matrices, but not necessarily unitary, because this is a Lorentz transformation question.
I guess this is the target we want, right?
This is what we want.
Target?
Target. Our goal.
Yeah.
This is our goal.
Yeah.
Yes.
So it must have some good properties.
Well, yeah. It says how we want the field to transform simply under Poincare transformations, Lorentz plus translation. And so this is the unitary transformation, and we then would have a representation of the Lorentz group, and then the field just turns into that, which is what it would have to be. And then we know what that is, namely that's a sum on sigma integral dqp, and it would be UL bar of lambda x plus a semicolon p sigma, and then a of p and sigma. So that's what the right hand is. But on the other hand, we also know that the field, being a linear combination of annihilation operators, we know how the annihilation operators transform under U. And so we are going to put that into play, and let me just say what that is. That means that this has to be sum on sigma integral dqp UL of x semicolon p sigma. So this is just that. And then it's U of lambda and A of p and sigma, U inverse of lambda and A. And now we know how those transform, namely, they go like this. The A's transform this way, the A daggers that way, or the B daggers that way. And so this is going to be a sum on sigma integral dqp UL of x p sigma, and this is going to be then EVI lambda p dot A sum sigma prime dj of sigma prime of W inverse of lambda and p, and then A of lambda p and sigma prime. So that's our task. How to choose. Our task will be how to choose the U's, the spinors, these coefficients, so as to satisfy this equation. The two right-hand sides are equal. And what we're going to do is use that identity that we worked out last time to rewrite this as an integral d cubed lambda p, and this is still UL of x semicolon p sigma EVI lambda p dot A. Let's see, don't we have a square root somewhere? I think I left out a square root. Hold on. Yeah, right here I left out a square root. So let's put in a square root of lambda p0 over p0. And now when we do this transformation, we get the square, it inverts this to p0, for p0 over lambda p0. And then some sigma prime dj sigma prime W inverse of lambda and p A of lambda p comma sigma prime. So all I've done there is something really just silly. I've just replaced dqp by d cubed lambda p times a ratio of energy of 0 components of 4 vectors, and that turns this into this. Okay. The corresponding thing for the negative frequency part is u of lambda A psi minus L of X, u inverse of lambda A. I want this to be a sum over L bar of dl L bar of lambda inverse psi minus L bar of lambda x plus the translation by A, and this one has two parts to it. We can think of this as the sum on sigma integral dqp. Let me see, I want, yeah, all right, so I'm going to, I don't know how many steps to skip here, because I feel as though if I put in all the steps, we're going to be here all night.
Oh, why is there, so in the argument of the UL, why doesn't that also become a lambda p?
Because I'm not changing variables, I'm just saying the dq
Oh, okay, I see.
lambda p over lambda p0 is equal to dqp over p0. I'm just doing that, so it's really simple. So maybe I'll put in an extra step here. This is we want it to be that, and that, all right, I'm going to add in some equations because it's better to have more than fewer. So we can think of this as some L bar, DL L bar of lambda inverse, some sigma integral dqp v L bar of lambda x plus a semicolon p and sigma p dagger p and sigma. By the way, the field theory was, of course, invented back, quantum field theory was invented back more or less in the 30s, and then it was worked on more and more, and then it wasn't until the early 60s, 64 or so, that there appeared a clear description of how fields transform under Lorentz transformations, and it was Weinberg who wrote these papers. And what he wrote, what we're doing now is essentially repeating what he wrote in those papers. So from one point of view, this is just, I've just translated this into an annihilation, into creation operators for the antiparticle. On the other hand, we know that that when the unitary transformation acts on the B daggers, then it'll turn them into linear combinations of B daggers with the D's, and that will give us this equation: sigma integral d cubed lambda p VL of x p sigma e to the minus I lambda p dot a square root p0 over lambda p0 some sigma prime p star j sigma sigma prime W inverse lambda p p dagger of lambda p sigma prime. And not sure why I've written that equation twice. Well, the second time it's a sum over sigma and sigma prime, I just interchanged. Here we're summing over sigma and sigma prime, so what we can do, if we want, is interchange sigma and sigma prime. And if we do that, I'll just do it this way, sigma prime, sigma prime, sigma, sigma prime, sigma, sigma. So if we do it, that's the way it looks. And so now what do we have? What we have here is let's see, I just think I am right. Let's rewrite this equation, changing variables. Now we're changing variables from p to lambda p. And so this thing is, let me just do it this way. This thing then is a sum lambda bar d, lambda bar of lambda inverse some sigma integral d cubed lambda p v lambda bar of lambda x plus a lambda p sigma b dagger of lambda p and sigma. Okay, so what we do now for the b dagger, for the antiparticles, is we require, after I've interchanged sigma and sigma prime in this last equation, we equate the coefficients of b dagger, lambda p, and sigma in these two equations. And that gives us the equation sum L bar, dl L bar of lambda inverse, v L bar of lambda x plus a, lambda p sigma is square root p0 over lambda p0, some sigma prime d star of j sigma prime sigma of w inverse of lambda and p VL of x p sigma prime e to the minus I lambda p dot a. Okay, so that's for the B daggers. If we go back here, we can do the same trick here. Namely, we want to identify the coefficients here of A of P, and in fact what we'll do here is also go from lambda P, from P to lambda P, and when we do that, we will get an equation, and in fact, let me write down that equation. That equation was sum L bar, dl L bar of lambda inverse, sum sigma d cubed lambda p, u L bar of lambda x plus a, now lambda p and sigma, a of lambda p and sigma. So we've just changed variables a little bit there. Yeah.
Also, in here, on the right, with the transformation, equation 16.
Yeah.
But why there's no transformation in this P? Since the transformation in this one.
Because we didn't do the change of variables. Here,
Okay.
all we did was use d cubed lambda p over lambda p0, is that equal to that? Let me, right. Okay, so now the question is, right, so it's not a change of variables, in other words. That's what I should have said. So in other words, to go from here, great question, to go from here to there, what we, right, I think do I have, no, well, if we, in the equation with the D's, we do change variables from P to lambda P. In the equation with the D lambdas, we are changing variables from P to lambda P. In the equation with the dW inverse, we're just replacing d cubed P by d cubed lambda P times a factor. So, let's see how this goes one more time. For the negative frequency parts, the field transforms this way, which is to say, D inverse, and we just changed to that, but now, now we change variables with the P, and so this P goes to lambda P, that P goes to lambda P, and this P goes to lambda P. So in one equation we do it, but in the equation with the W's, we're not doing that. And just as well, because we would have to screw around with this P. We don't want to do that. Okay, so the upshot is, after everything, we have two equations. This is one, and the other one is some L bar, dLL bar of lambda inverse UL bar of lambda x plus a lambda p sigma is the square root p0 over lambda p0 some sigma prime d star j sigma prime sigma w inverse of lambda and p VL of x p sigma e to the I lambda p dot a. So it's I, not minus. So those are the basic two equations. Weinberg has sigma and sigma prime different, and I think he's got a typo. I think what's in the handout is right. But you shouldn't trust anything either of us writes, and so if you see a mistake, tell me. Send me email. Yeah.
What property are we using that allows us to equate coefficients here?
Oh, if you have two equations with operators, you can identify the operators are linearly independent.
Okay. So we're using.
So it's as though we had totally. I'm treating the operators as though they were orthogonal vectors,
Okay.
and they certainly are. They're
Okay.
they're even more than that.
Okay. Yeah. So what orthogonality property is it that we're using?
But you get a candy and
Yeah.
so do you. What?
So then what's the orthogonality property that we're using here? Is it the fact that two
Well, all right.
operators
It's
or a creation and annihilation operator on different modes commute? Or is it
all right. It's alpha b dagger of piece. In other words, suppose this was alpha of p and sigma
Yeah.
summed over p sigma. Let me not distinguish.
Sure.
Is equal to the sum beta of p and sigma b dagger of p and sigma. Well then, since these guys are totally unrelated one to the other,
Yeah, but what's the relation that tells you that they're unrelated? Like, I don't know,
Well,
like if you have a bunch
Christ,
of trig functions,
I mean,
you can
all
use
right.
the fact that they're orthogonal. What's
on
that?
any state, this guy adds a particle of momentum p and a spin sigma. If you change p and or you change sigma, then you're adding a particle of different momentum or different spin.
Okay,
So you're mapping an arbitrary vector into two different vectors.
yeah, sure. Okay, so, I don't know, think of it as like acted on the vacuum and take the inner product with some state or something like that.
Right, you could, since these are you could take any state on the right, any state on the left, and
Yeah, I think if you acted on the vacuum and you take the inner product with like a p prime sigma prime, that would do it.
all right, if you're happy with it, fine. It struck me as being manifestly true, but I didn't try to work out the logic.
Sure, I see. Yeah, but I see.
All right, we're all happy, good. But if you see a typo, tell me, because, the fact that I spent several hours producing this, and the reason I LaTeXed it was for two reasons. One was to make it nice for you, but the other is that I didn't think I'd get the indices straight unless I made it clear, unless I had something that was clear enough to look at that I could make changes and see what the changes were. Because this is really, anyway, so this means alpha of p and sigma has to equal beta of p and sigma. Okay, so, but we're not really done yet. Weinberg does one more thing, namely, this is sort of an awkward form. What we want to do is we want to multiply both sides by d of lambda and d super j of w and wait, I don't think we want a star on both of these. Right, the star on the one on that one, but no star here. This one has no star. Right. Otherwise, they're the same. The only difference are a minus sign here and a star for the antiparticles, a plus sign and no star for the particles. Let me remind you then, these are non-unitary square matrices. These are unitary square matrices that are representing rotations, Wigner rotations, so they're unitary. These are square matrices representing Lorentz transformations and not unitary, but they're the matrices that we talked about in the first week or so of class when I used my group theory notes, which are on the website. So what we're going to do is we're going to multiply these equations. First, sum L bar dl, oh wow, I have a prime. Oh, I guess this is okay. dl prime L of lambda dl L bar of lambda inverse u L bar of lambda x plus a semicolon lambda p sigma. So what I'm doing is I'm acting on this bottom equation, multiplying from the left by another d, and the d is L prime L, and then summing over L. Well, this just gives you d inverse, and so this just gives you delta L prime L bar. And so this is actually something very simple. It's just that L bar turns into L prime. On the other hand, when this thing acts to the right, we get a real mess, namely square root of P0 over lambda P0, sum sigma prime L dj sigma prime sigma W inverse of lambda and P dl prime L of lambda UL of x semicolon P sigma prime EDI lambda P dot A. Okay, but you see this is taking shape because now we have DL prime L next to UL, and that's something that we want. We now act, well, if we act on the antiparticle equation in the same way, shall I write down the whole equation or just tell you what's different? Maybe it's, how are we doing? I think we have time for me to write down the whole equation. So now this is sum L bar L dl prime L, again lambda dl L bar of lambda inverse V L bar lambda x plus a lambda p and sigma, and that is going to once again give us a Kronecker delta. So this gives us V L prime of lambda x plus a semicolon lambda p and sigma, and on the other hand it also gives us a square root of p0 over lambda p0, a sum on sigma prime and L, d star j, sigma prime sigma, W inverse of lambda and p, d L prime L of lambda, VL of x semicolon p sigma, e to the minus I lambda p dot a. Okay. So these equations are half what we want and half what we don't want. But the way to fix it is to multiply both equations from the left by the square unitary matrices that represent Wigner rotations. And I'll do that on the whiteboard. Okay, now I'm gonna replace the big rotation, instead of calling it W of lambda and P, I'm just gonna call it W. This is just one W. And so we multiply both sides by this dj of W. What we have here then is sum on sigma of dj sigma sigma bar of W on U L prime of lambda x plus a semicolon lambda p and sigma. And this will be acting on that right-hand side, which is huge. It's square root of P0 over lambda P0. And now it's a sum sigma prime sigma and L dj sigma prime sigma of W inverse. And now this thing, which I write in second position, dj of sigma sigma bar of W dl prime L of lambda UL of x semicolon P sigma prime, and then the phase factor e to the I lambda P dot A. Okay, but of course, this times that is just the identity, because this is because it's W inverse, or just as, this is a representation of the rotation group. So d of W inverse times d of W is just d of the identity, which is just the Kronecker delta. So this just gives us delta sigma prime sigma bar, and that turns that sigma prime into sigma bar. And so what we have then is that this thing is equal to square root of P0 over lambda P0 sum L dl prime L of lambda UL of x semicolon P sigma bar e to the I lambda P dot A. Okay, so that's a very nice expression. That says that the rotation matrix on the Lorentz, on Poincare transform spinner should be a factor times the Lorentz matrix on the ordinary spinner times a phase factor. If we do now the same thing with the, on the antiparticle equation, what we have is sum on sigma d star j sigma sigma bar of W v L prime of lambda x plus a semicolon lambda p and sigma. And so I'm working on that blackboard, the last part of the last blackboard. And this is then square root of P0 over lambda P0 sum on sigma sigma prime and L d star j sigma prime sigma W inverse d star j sigma sigma bar W d L prime L of lambda VL of x, p, and sigma prime e to the minus I lambda p dot a. The dot, of course, is a Minkowski dot product. Okay. This just gives us d star of the identity, which is just delta sigma prime sigma bar. And so this turns into square root of P0 over lambda P0 sum on L, d L prime L of lambda, VL of X, d sigma bar. Okay. So now we have two really important equations. And the equation is this thing is equal to that, and then the other one that's really important is that this one is equal to that. So those are the key equations that determine how the spinors transform, or as Weinberg calls them, the coefficient functions, how they transform, how they must transform
Are we missing the phase
if the
factor?
fields are transformed correctly.
Are we
Huh?
missing the phase factor in the bottom?
What?
Are we missing the phase factor in the bottom one?
Yeah, probably. Yes. E to the minus I lambda p dot a.
So is that the only difference, the minus sign and the phase factor?
All right, let's think about it. What is the difference? Going from particle to antiparticle. The rotation matrix gets complex conjugated.
Does that stay down there? Because that one isn't in the final result.
This is the equation for the antiparticle. This is for the particle. The rotation matrix gets complex conjugated. The translation phase factor gets complex conjugated. And that basically is it. Let's see, I guess you're going to run out of... Oops, sorry.
Professor,
Yes.
what this expression tells us?
What is what?
What is this tells us? What does this tell us?
What does this tell us? Is that what you're
Yes,
saying?
yes.
Oh, everything, apart from a couple of phase factors. And in fact, this, anyway, in the notes, these are equations 25, after one, I guess, I don't know, I may have cleaned them up slightly by changing a bar or dropping an unnecessary bar or
Why do
prime.
we lose the complex conjugation when we go from? Because in the
Why is
antiparticle, the antiparticle starts out that being complex conjugate, and then the final result in the bottom, that new D matrix, isn't it complex conjugated?
No, the D never got complex conjugated.
D. Oh, there's a difference in the D and the DJ. I'm sorry.
Just asking questions to get candid. Okay, so translations. To figure out what the spinors are for translations, it's pretty simple. What we do is we just set.
Okay, I have one more question. You don't have to use the K. But so this D without the K. So it's an infinite dimensional representation of the Lorentz group, but it's not.
No. This is a finite dimensional, non-unitary representation of the Lorentz group.
Okay, so these VLs.
And these
okay.
are unitary representations of the rotation group.
Are they finite dimensional or infinite dimensional?
Yeah.
They're finite?
These are the ones you
Okay.
learn about in quantum mechanics.
Oh, okay. Okay.
E to the I theta dot sigma over 2.
Yeah.
Somebody tortured you with that when you were young.
What? Yeah. While you did, yeah. It's just hard to keep track of the superscripts and.
Yeah, well, as I said, this is one of the hardest parts of Weinberg. Most of the really hard parts of Weinberg you can skip because there's super deep thoughts that only he has.
What's the dimension of L? Well, how many L's are there?
Huh?
What's the dimension? How many L's are there? What does L run from?
Well, all right, for a Dirac field,
Okay.
L goes over 4 values. And the sigmas go over 2 values, up and down.
Hmm.
Yeah, so I feel like we have 3 things that are representing the spin. And I want to know why they're different. So we have J in our rotation matrices because we've used the representation of the rotations.
This
for
is
spin
okay.
J particles.
Yeah, this is
We also have sigma. We also
these
have L.
are fields and particles of spin J is what one says.
Okay, but then furthermore, we talk about sigma as being spin too, right?
Sigma is Z component of spin.
Sigma is a Z component. Okay, sigma is a Z component, and then you were also saying L is like spin.
Yeah, like, but I said like. I didn't
Is
say.
it this isospin thing?
No,
Okay,
God,
it's not
no,
okay.
no, absolutely nothing like
Yeah, okay.
isospin here. Good catch. So, the L's are Lorentz indexes.
Okay.
So is that just?
So, for example, if we had, well, let me not go in that direction.
Okay, but if you're saying L is running, it's 4, so it's a 4x4 matrix. I mean, is it just the
For
defining
a Dirac
representation?
field, that's a 4x4.
So is it just the defining representation then? Is
Huh?
it just the defining representation? Is those
Well,
I'm glad.
if you had taken my 467 last semester, we would have talked about the representations of the Lorentz group, but they're in the notes that's on group theory that are posted on the class webpage. There are basically, there are two representations of the Lorentz group. Two 2x2 representations that are inequivalent. And we call them left-handed and right-handed. For a Dirac field, we put them both together, and so the Dirac field uses a D that's 4x4, but is a reducible representation of the Lorentz group.
Because this is block diagonal.
Yeah,
It's the direct product,
yeah.
the direct sum of those two.
Yeah. Okay, we have essentially Zippo time left, but we take these equations that we say are really important, and we set p equal to 0. And we set the D matrices equal to 1. So in other words, we're taking the Wigner rotation to be the identity, so this is just the unit matrix. We're saying that the lambda matrix is the identity. P is just m and 0. And what does this turn out to be? This thing collapses into, if we do, well, first of all, this factor is unity. This thing turns into U sub L of the displacement A, P, and sigma is U sub L of P0, momentum 0, P and sigma e to the I P dot A, and the other one is V sub L of A, P, and sigma is V sub L of 0, P and sigma e to the minus I P dot A. Okay, so the spinors just depend upon space-time through phase vectors. And consequently, we can deduce, or we have deduced, that the spinors are really very simple. The x dependence is very simple. 1 over square root of 2 pi cubed UL of P and sigma e to the I P dot x and VL of x P and sigma is, to write it differently, 2 pi to the minus 3 halves VL of P and sigma e to the minus I P dot x. So the space-time dependence of these spinors is very simple. The 2 pi to the 3 halves, of course, is a convention. And the result is that the fields are really Fourier transforms, namely psi plus L of x then is 2 pi to the minus 3 halves integral dqp e to the I px ul of p and sigma a of p and sigma and psi minus is 2 pi to minus 3 halves integral dqp e to the minus I p dot x VL of p and sigma b dagger of p and sigma. And remember, we're using the antiparticle creation operator because we want to have a theory that treats charge in a sensible way. Okay, next time we'll start with these red and green circled equations and consider the case where, well, first of all, we'll make use of the fact that we know the space-time dependence of the spinors. We'll then consider how they must transform onto boosts according to these equations, and that will tell us something very simple. Then we'll go back to these same equations and see what they tell us about how the spinors transform onto rotations, and that will tell us essentially, that will give us key equations that determine the structure of the spinors up to a couple of phases that are arbitrary. And as I said to you, quantum field theory went into the mid-60s before anybody actually wrote phys-rev articles that explained this. In other words, previous to that, people just waved their hands. They knew what the Dirac action had to be. They were doing quantum electrodynamics. Dirac had worked out the Dirac equation. That was right. So you knew what the action had to be, what the interaction had to be in quantum electrodynamics, and so people just used it. And I remember I don't know, must have been the mid-70s when I finally came upon Weinberg's papers, which he had written 10 years earlier in the phys-rev, explaining this material here, and it's the first description. And books are still being written that ignore this treatment and get the spinors wrong. And in fact, in many books, the spinors aren't really explicitly written. So, for example, Peskin, for example, I think he doesn't say anything wrong, but he never tells you what the spinors are for the Dirac field. Schwartz, in a very new book, in its second edition even, gets them wrong. I wrote to him. He said, "Why do you say that?" I said, "Weinberg has a different expression, and he derives them." No reply.
What did you work on when you were in graduate school?
I worked on quantum optics. I worked on quantum optics, but I'm more interested in particle theory.
Okay.
So I just, my day job was quantum optics, my night job was particle theory. But I was actually, let's turn this off before I say